Given any 2 points on the coordinate plane, we can draw a line between them, and in order to find the equation of that line, we can use what's called the point-slope form. And one of the things we like about that is that as soon as you know the slope and you know the coordinates of either one of the points, you immediately know the equation for the line. So the general form is y minus y sub 1 is equal to m times x minus x sub 1, where m is the slope of the line and x1, y1 is any point on the line. So whereas x and y represent the general points on the line, x1 and y1 represent specific points. So in this case, we could say that the equation for this line is, because the slope is negative 1.01, we can plug in point A, and we get the equation y minus 4.2 is equal to negative 1.01 times x minus the x value of A, 0.56. On the other hand, if we plug in B, we get y minus 2.1 is equal to, again, the slope, x minus, in this case, the x value of point B, or 2.64. If we were to expand either one of these and put it in the form y equals mx plus b, we would end up with y is equal to negative 1.01. So the slope shows up in both forms. But in this case, our number here would represent the y value of the y-intercept right here at 4.77. So this works certainly when we have a line that is horizontal. We end up with y equals 0x plus 2, which would just simplify to y equals 2. And again, up here we would end up with y minus 2 equals 0, y minus 2 equals 0. On the other hand, if we have this line, which is actually no longer a function, this breaks down because we have an undefined slope. And so we no longer can use either of these forms of equation. In fact, we would have to use, in this case, x is equal to 3. But we would no longer be dealing with a function in that case. So the point-slope form is an important one to keep in mind. It actually shows up in all kinds of settings and is the easiest for us to work with, especially when we're moving into differential calculus.